Hi, everyone. Today we're going to look at going through a full trigonometry review. You've previously gone through and reviewed all your right angle trig, so all of our SOHCAHTOA. Now what I want to do is I want to open it up and move away from right triangles to examine any possible triangle that you could exist. So take a look at the first problem. What we're going to do is we're going to solve that triangle, and we're going to solve a number of them today, 3 of them. The first triangle is going to be triangle DEF with those properties. So first thing I would always recommend you do is construct your triangle. Now, I'd like you just to notice the way I would go through and construct your triangle. A real common practice is to simply draw the same triangle over and over again and simply label it with different properties. So if I was to give you like the next triangle, and that was triangle DEF, you would basically end up drawing the same triangle over and over again, but labeling angles and sides differently. That can get us into a big issue, or address a big issue, which is, how do we know whether that triangle should be acute, whether it should be obtuse, whether it should be right? How do we deal with the relative nature of side lengths and angles? So one of the things I want you to maybe notice is your past practice. Perhaps you ended up drawing equilateral triangles all the time, or something that looked like it and labeled different, or looked like it, an isosceles triangle, and labeled it different. But very few of us naturally would draw something that looked like this for triangle DEF, and then chose to label that. So what we want to do is we want to take our time as we work our way through. What we're really going to do is we're going to now use the properties of the triangle to start constructing relatively accurate diagrams. So first thing that I would always recommend to you is build up from your angles. So I have angle D that is a 42-degree angle. So I'm going to draw something that looks a little bit smaller, or pretty close to the diagonal of a square. Diagonal of a square is 45 degrees, so 42 is pretty close. That is now my angle D. And so I know that the rays of angle D could go on to any determined length. What I'm now going to do is I'm going to start to put in all the lengths that I've been given in the problem. And so I've been given side E and side F. Well, if this is angle D, then side E and side F have to exist as the rays of D. So maybe I extend this ray to what I would estimate to be 6 centimeters. Like, I'm just going to call that 6 centimeters. And then what I can do is I can extend this bottom side a little bit shorter than that, and I'll call that like 4 centimeters. If that was the case, then there is only one possible triangle that I could construct, which means that I would now be able to connect these two rays, and I would be able to label my diagram. The side of 6 must make this vertex E, and the side of 4 must make this vertex F. And so there is my diagram. Hopefully your diagram looks somewhat similar. Now, in order to solve that triangle, what we need to do, we need to go through and find everything that's missing. So we need side D, angle F, angle E. Now, perhaps you've got in your background that when we see a triangle with this given information, we should know our starting point. We should know right now that we're going to need to use cosine law, because we see on that diagram that you have been given a side, an angle, and a side. That triangle would often be referred to as a side angle side scenario. That means cosine law. Now, we have to make sure that we get side angle side down. that doesn't mean a side, any angle, any side. What side angle side actually refers to is a side, another side, and the corresponding angle, that contained angle. So when we see that information, we know we can use cosine law. And so, just since this is a review, we're going to end up writing down our cosine law. So, for me, I can now find what side D is. So, I've got D squared. As a review of cosine law, we should know that cosine law is really based on Pythagorean theorem. So, D squared has to equal the sum of the squares of the other two sides, E squared plus F squared. And now we need to adjust it. So we need to adjust it. This triangle might not be a right triangle. So we need to adjust it by subtracting 2 of those EFs cos of the contained angle. And there is our version of cosine law. You'll notice what you end up having. Pythagorean theorem adjusted. Now, what I put in green, I would never have to see a part of a solution. So, my next line could be my substituting 6 squared, 4 squared, minus 2 times 6 times 4 cos of the angle. Now, I recognize on that line that I have 3 terms on the right side of my equal sign. I can collect 2 of them. But I can't collect what's left on the right side because I have unlike terms. Now I need to solve for D. That means I need to take the square root of that whole thing. Now, what I'd like you to notice is I changed colors on that last line. The only thing you would have to show me in your solution as a first line is that blue line. However, I'm going to put a star beside the other line that I would recommend you put down. I don't think that really slows you down too much. However, that line with the star beside it, if you were to look back on the original triangle, you could probably confirm whether you substituted everything incorrectly from that starred line. If you're jumping straight into the blue line, maybe we miss that and we can't see it as easily. My recommendation to you, give me the blue line, or that starred line, then give me the blue line, and now let's convert it to the way we talk about it. So when you go ahead and calculate that, we're now going to get a value of about 4.04. We're finding a side length, so we round it to 2 decimal places. And now we put on our units. So we've been able to work our way through and now solve for D. And now that we have D, now we have a side and its corresponding angle. We do not need to use cosine law again. Now we can jump in and start using sine law. So here's where things get interesting. Okay, I just cleaned up our screen a little bit. So now I have a decision to make. I need to go through and solve for F or E, and I'm going to use sine law to do that. So maybe I take a look at it and I say, I'm going to find alphabetically E, just because E comes first alphabetically. And so I can now take my sine law, which would say sine E over its corresponding side, must equal the sine of 42 degrees over its corresponding side. There is my application of sine law, that the sine of any angle compared to its corresponding side is the same throughout a triangle. So, for me to go through, there's my application of sine law. Now I can isolate by multiplying out my 6. And now I'm going to go ahead and I'm going to push some buttons on that. You can show me this line that E is the inverse sine of that whole mess. Or you can jump straight to a value for E. So you never have to show me that green line. However, if you like to include it, feel free. And we should get an approximate value of 84 degrees. We're finding an angle, so our default rounding is to the nearest degree. We then go through, we have E being 84. We can then use that the sum of any triangle is 180. And so therefore, for me to find that angle F, I would then take 180 and subtract the other two. And so F is going to give me 54 degrees. So we come in and we're able to work our way through and solve, and we're good. So hopefully everything matches up if we went through that process. Okay, we got to step out and we got to take a look at something now. Okay, so what you'll see on your screen right now is I've just gone through and I've gotten rid of all that extra work just to make a little bit more space, and I've listed out what we just found on that triangle. Remember, though, that after we found side D using cosine law, we had a decision to make, whether we wanted to find angle E or angle F first, and I simply chose angle E because alphabetically E came first. Well, what if we had have chosen to find angle F first? So I'm going to very quickly just go through the process of finding F first. If I then went through to find F, I could say that the sine of F compared to its corresponding length of 4 has to equal the sine of that angle compared to its corresponding side. So we could go through and find that. You would then have that the sine of F is 4 sine 42 degrees over 4.04. And as we stated before, you can go through and you can show the inverse of that whole value if you wish. But as I said, that would never be needed. You can simply calculate 4 sine 2 divided by 4.04, take the inverse sine of it, and work our way through. And we should see then that angle F is approximately equal. Okay, wait a second then. I want you to notice that right off the bat, we have different answers. Now, if I was to continue through on that process then and say, well, then if I wanted to find angle E, I know that angle E is 180 minus the sum of the other two. So that's 180 minus 83. That's 97 degrees. And I'd like you to notice again, that's something different. So as we start to take a look at it, why did we get two different answers when we should have gone through and got the same triangle? You might recall back from grade 11 that you went through and you examined something called the ambiguous case of sine law. Sometimes coming out of grade 11, we have this mistake in terms of concept that we think that we have two different triangles, and that's what the ambiguous case of sine law is. I want to make sure that we're very good with that. There are not two different possible triangles that could be created for triangle DEF. Notice, if we look back at our diagram, if I have a side length of 6 and a side length of 4, and I form those two side lengths at an angle of 42 degrees, then there is only one triangle that could be formed. I connect it with side EF, one triangle exists. So I can't have two possible measurements with this. So what happened then? The key was at this step. That when we used our calculator and we went backwards to find the angle and said the inverse sine is equal to, our calculator misled us. Or at the very least, we maybe didn't understand the assumption that our calculator makes. So what we need to make sure we do is that we have a full understanding of what's happening. Here's the issue, and I'd like you just to push some buttons into your calculator really quickly. I'd like you to punch in sine 30 degrees for me. You'll notice when you punch that in, you get 0.5. And so if we wanted to go backwards, then your angle, and we'll just call that theta, if you ever took the inverse of 0.5, your calculator is going to give you 30 degrees, which should make sense. If the sine ratio of 30 degrees is a half, then when I go backwards and do the inverse sine of 1/2, I should get its angle, 30 degrees. Well, now I'd like you to punch into your calculator the sine of 150 degrees. Something interesting might pop up, and perhaps you can recall this from last year. Well, now when I go and do my inverse sine of 1/2, my angle spits out 30 degrees. Here's my problem. My original angle was 150 degrees, but my calculator is telling me that the angle was 30. My calculator is designed with a set of rules. It's programmed to follow certain rules. And what those rules are is whenever I take the inverse sine of some value, if my calculator can give me an acute angle, an angle less than 90 degrees, then that's what it spits out as an answer. But you can see, though, that some obtuse angles, in this case 150 degrees, could have been the angle that we were dealing with. And so what we need to make sure we do is we don't become reliant or too trusting of our calculator. Instead, what we can do is we can put together a process, and that process will ensure that our calculator never misleads us. So I want to make sure that we are good when we take a look at this problem, that our first solution was actually incorrect. If you take a look at any triangle, we should be good that there could only ever be one obtuse angle. And so what I want to do is I want to examine that triangle a little closer. So let's go back and let's take a look at that triangle with neither angle E or F being solved for. This is where I got to the point where I had to make a decision as to which angle I was going to look for first. And you may have come out of grade 11 with one key idea in your head. Always find the smallest angle first. Now, maybe we didn't have a full grasp for why we do that, but maybe now we can see that when I take a look at angle E and angle F, I don't know if those angles could be obtuse. Or at the very least, I don't know if there is an obtuse angle in that triangle, or if all three angles are acute. However, I do know that big sides make big angles. So if I have a really big angle, then it is going to make a big opposite side versus small angles making small opposite sides. So when I go to examine my triangle, I can then take a look and say, well, if there was going to be an acute angle, I don't know for sure, but if there was, the only possible obtuse angle, if there was an obtuse angle, the only possible angle that could be obtuse would have to have the largest opposite side. That means that angle E could be obtuse. I don't know yet. But what I do know is that every triangle can only have one obtuse angle. It can't have two. You can't have two angles that are greater than 90 and then all three angles add up to 180. So if I make the decision to solve for the smallest angle first, then I'm going to find angle F, because I know that when I get to the point and I say that I am going to take the inverse sine of that big ugly mess, I know that what my calculator spits out will be correct. And then I can use the sum of my angles adding up to 180 to generate whether that largest angle should have been acute or obtuse. In this case, I find out, oh, wait a second, angle E is actually obtuse. And I ensure that my calculator doesn't lead me astray. So what you just examined was the ambiguous case of sine law and how our calculator can get us in trouble. After this, I think we should be able to pick up the pace a little bit. Just remember that if you have a choice, always find the smallest property first. Okay, let's move on. So what you'll see on the screen now is we need to solve for triangle XYZ, where we are given those properties: angle X, angle Y, and side X. So the first thing I always do is I start to build my triangle from my angles. So I'm going to create angle X, which has a bottom ray and a top ray. It is an angle of 64, so I'm going to make it be a little bit bigger than my perfect diagonal. Now, again, I know that those rays could have any length to them. The other property I know, and I'm going to jump down to the fact that I was given a corresponding side, is I know that side X, if it was 14 meters, and I'll just call it that, has to exist opposite angle X. That means that angle Y would have to be at the end of one of those rays. So maybe I just declare this angle Y. I know that angle Y, 27 degrees, would be a relatively small angle. That means then that if I was to stretch out, that would now be the length of X. So all I'm going to do is I'm just going to clean up my diagram a little bit, and we can get rid of side X, and I'm just going to change my Y back to the same color so we can see a clear diagram. If I was to take a look at those as my features, we should be good then that I can only have one possible triangle. Why is it one possible triangle? You can maybe see based on what would be the first thing that you would solve for. Notice, and I would hope, that everybody was solving for Z first, because if we know two angles, then our third angle is fixed. And so we should be good that angle Z is going to be 89 degrees. And so now as we take a look at that triangle, we need to solve for side Y and side Z, and we can use sine law to go through and do that. Now, since I'm not finding an angle, there really is no ambiguous case to sine law. However, if you're looking for uniformity, then maybe just the easiest thing to do is to always find your smallest stuff first. So maybe then, since I see that angle Y is 27 degrees, angle Z is 89 degrees, I'm going to find side Y first since it comes from the smallest angle. So my Y compared to the sine of its angle has to equal side X compared to the sine of its angle. And so I can then multiply out my sine 27. And just to clarify on solution, I would need to see both of those blue lines. My first line is the application of sine law. My second line is the exact value of what y is. Now, we don't talk about that, so we would go through and push some buttons, and since we're finding a side length, we would round off to 2 decimal places, and we get about 7.07 meters. Okay, we should be able to go pretty quickly then to find z. Z compared to the sine of its angle has to equal, and let's keep using the x's. Don't jump over and use y because y is rounded. Everything with the x's was given, so you know that it's correct, and it's exact. And so if we push some buttons to work our way through and solve, then we know that z is approximately equal to 15.57 meters. There we go. A quick solving of triangle XYZ. Now, I'd like us to take a look at our last problem for today. Us going through and solving triangle ABC, where A is 54, B is 22, A is 19. This was a problem that a lot of us tend to throw in the category of ambiguous case of sine law, and we're actually incorrect on that. This is a situation that deals with the information given and the possibility of my number of triangles. I'm going to go through and I'm going to construct that triangle as we have for the previous two. I'm going to begin with my angle. Angle A is 54. There's my 54 degrees. I know that those rays could go on forever, and I'm really going to draw them on forever in both directions. Now, I've been given side B. Side B is 22, so it would have to be one of those two rays. So what I'm going to do then is I'm going to fill in, and I'm just going to call that length 22 meters. Now that I look at that third property, I've been given that side A is 19. And so, if angle A is 54, then I know that side A must exist across from it, and we have a very natural tendency to want to then call this 19. And now I can connect the bottom of angle A with the end of side A, and there's my triangle. The side 22 is given, which means this must be B. That makes this C, since the name of the triangle is ABC, and I can then eliminate the rest of that ray. So, a very common approach for us to being able to go through and solve. However, I want us to notice that we made one big assumption as we went through. When I went and I drew on side A, I made the assumption that side A has to come out. So all I'm going to do is I'm going to eliminate side A again. I made the assumption that side A has to come on this angle. Notice in my properties, there's nothing that defines the size of angle C or angle B. And so this is where we naturally want to draw something that looks like an acute triangle, because we tend to think of acute triangles as like normal triangles. But what if side A shouldn't have been in that position, and the bottom of angle A was still just a ray? Couldn't it be possible that angle A should have come in that way, and instead B should have been in this position? I want you to notice that that satisfies the given information as well. And so what we really encounter in the problem then is that there's not enough information given to nail down this as one particular triangle. We could end up with a couple types of triangles. So what I want to do then is I want to kind of talk about how we construct this triangle, maybe in a little bit of a different way. There's the bottom side of my angle A. We see that side A was 19, and we can then go through and connect those, and then make the bottom side of A solid, and there's my triangle. Now, what I want us to imagine at the very beginning was that there was no particular angle that side A had to be laid down in. So rather, it just kind of hung here, like straight down, and that's a horrible straight down, but like straight down. Well, maybe we see then that if that was my 19 hanging straight down, then what I'm going to do is I'm going to put that angle on. And so I now take that side and I rotate it outwards so that my blue line, the bottom of it, fits with the bottom of angle A. And that's what allows me to construct that triangle ABC. However, there's nothing that said that I had to swing out side A in that way. Rather, I could have swung side A in this way and connected it with the bottom of angle A, and I could have formed that triangle. Maybe that was where my position of B should have been. So what I end up getting out of that are two possible triangles. I actually have this triangle that could be triangle ACB, where B is 22, A is 19 with this angle. Or I get this possible triangle of ACB, where B is 22, A is 19 with this possible angle. Two possible triangles that satisfy the given information. Now, I want to talk about some details to that on how can we recognize then when I have two possible triangles versus when I can only have one. So, if we were to look back at the construction of that, the key component is the fact that that given side that I've been given, that is corresponding to angle A, is my side length of 19. And it is the way this 19, the corresponding side, compares to the other given side. So what I'm going to do is I'm going to change up the information a little bit. And instead of having side A be 19 meters, I'm going to now change that to a side length of 25 meters. And I'm going to walk through constructing that triangle the exact same way. So angle A is 54. There's my 54 degrees. I can extend this side and call that 22 meters. Now, I have my side length that is 25 that is dangling down. I haven't put it at any particular angle. But I can see that I could swing that out in this way so that side A actually lies there. And now I could extend the bottom of angle A, and there would be my triangle. A, C, and B. I'd like you to notice, though, that we don't have the ability to swing our line in the other direction. Watch what happens as I try to take that side length that is 25, and I try to swing it up. Notice that that side length of 25 is longer than the other given side. And since it's longer than the other given side, there would actually be a point where I could lay it directly on top of side B, and I still haven't got the bottom of it up to the bottom of angle A. That the only way that I can get it to be on the same level as angle A is to swing it past that vertex. Well, now it lies in that spot. Here's my problem. As soon as I have to rotate it past vertex A, angle A doesn't exist anymore. So, I only end up with one possible triangle. So, what conclusion can we draw? You have to take a look at the given information. If I am given two sides and one angle, and one of those sides is the corresponding side of the given angle, then I need to compare it to the other side. So, when I took a look originally, side A is the corresponding side. It is smaller than the other given side. Therefore, two triangles. However, when I changed that information and I made side A larger than the other given side, then I can't swing that side in both directions. I can only swing it out, therefore, one triangle. So, if we can keep that idea in mind as we go, then we should be good. Notice, this is where a lot of us put this idea in our head last year and said, oh, that's the ambiguous case of sine law. This has nothing to do with sine law. This has everything to do with you were given properties to form a triangle, and given those properties, multiple triangles could exist. So all I want to do is I want to finish off this problem showing you a way to go through and solve for both possible triangles in a pretty efficient way. Okay, so if we go back to our original diagram then, let's take a peek because we've got a few things to label. That if I know that side A is 19, then side A could sit in the red position, or it could sit in the green position. But I do know that both of those would have to be 19. Now, here's a problem with my labeling. I have two vertices sitting at B. B cannot be in two different positions at the same time. So what I do is I use subscript. Potentially that's B1, this would be B2. Now when I take a look at that triangle or that diagram, I see that I need to solve for my two possible triangles. So what I do then is rather than use the subscript, I give the title to the triangle. So I know that when I use sine law finds acute angles first. So I have angle A and side A. That side A could exist in either spot. I can use that to find angle B because I've been given side B. However, I can't use it to find angle B2 first because angle B2 is obtuse. So I'm going to use it to find angle B1 first. Now, if I put a little heading down, then my heading allows me to be efficient with what I need to write. So I'm going to work inside triangle ACB1. And when I do that, I don't need to use my subscript anymore, because in that triangle, there is only one angle B. And so sine B is going to equal 22 sine 54 divided by 19. And so we can jump some steps on that and we can get our solution. And so 22 sine 54 divided by 19, now take the inverse sine of that, we should get that we are approximately 70 degrees. Okay. At that moment, I can find a bunch of things in my diagram. I could then go and stay inside that same triangle and find angle C and side C, or I could jump triangles. What I'm going to do is, since I put that heading on, I'm going to go and just finish off triangle ACB1. Okay, now that I know that B is 70, I can then find angle C. I know that angle C is 180 minus the sum of the other two. So that's 180 minus 124, and that's going to give me 56 degrees. Now that I know what angle C was, I can then find sine C by using sine law. I'm going to go back and use the given information because I know it's exact and it's perfect. I need to see all those blue lines in my sine law, and now I can calculate an approximate value for that. And I'm going to get approximately 19.47 meters. I have now solved for triangle ACB1. I'm going to do a quick check and make sure that big angles mean big opposite sides. So my biggest angle in that triangle was B, and so it had a side length of 22. My next biggest angle was angle C at 56, so it had a side length of 19.47. My smallest angle, 54, gave me my smallest side at 19. Everything checks out. Okay, you do not have to do this, but I'm going to do it on my diagram. I'm going to actually label angle B1 because maybe we can see something on our diagram. I'm also going to go through and just highlight that on that diagram, I actually have a third triangle. And I just want to put this in a different color here. That this triangle that you see me highlighting right now, it doesn't actually exist because that triangle would be B2, C, B1. It would have two B's. But I can use that to help me solve for the other triangle. Since that triangle is isosceles, then I know that of the two equal sides, their angles must be equal. And that's what's going to allow me to jump into triangle ACB2, because I know then that angle B is 180 degrees minus my 70 degrees. I know that it's 110 degrees. Now that I have that, I can finish off solving for the rest of that triangle. So what I'd like you to do is pause the video right now, work your way through, and see if we can find our matching C values. Okay, we should be back. And so to find C, I'm going to take 180 minus the sum of the other two. So that's 180 minus 164, and I'm going to get a really tiny angle of 16, which should make sense. That's a really tiny angle up there. Now I can use sine law. Since I know angle C, I'm going to go back and use my given information because I know it's exact and it's correct. And then I can push some buttons. Now, I am finding side C. And side C came from a really tiny angle C. So I'm expecting to get a pretty tiny answer for side C, and that matches up. So hopefully today, what you take from this is you have a little bit better understanding when to use sine law and cosine law. We can go through and solve triangles, whether there's one possible triangle or two possible triangles. And also, we now have a greater sense of why we need to find smallest angles first and the appropriate use of the ambiguous case of sine law. Okay, your job now, jump in and get some practice and make sure you're good to go with sine law and cosine law. Good luck.